Hello, everybody, and welcome to what are we going to call it? We want to call it the Rapid Designs Put Stuff on the Internet thing. That's what we're doing tonight. Guys, my name is Sam. I was a structural engineer in the past, and I'm going to be talking to you guys tonight about a little bit of knowledge thing. I'm going to try to get over here in the vertical shot too, so that everybody is happy on the Instagram side. But yeah, I'm going to use this whiteboard, and we're going to talk about a few structural things today. It's been a while since I put some structural stuff on the YouTube, so here we go. I had a conversation with a particular customer the other day with this particular design was we're designing this ADU for somebody, and they were getting very creative with the design. Things were going not to plan, trying to get stuff from the city, and they ended up like just trying to get creative with how to get enough height for a loft and stuff. And the idea was thrown out there. I was like, hey, well, why don't we do one of those cool Gambrel roofs, because those allow for a lot of internal volume, but they don't necessarily involve a second story of walls. So they threw that idea out there, and I said, that's not bad, except for the fact, that you're trying to vault the inside of the ceiling, and you don't want to do that. And they were like, well, why not? And I was like, well, there's a whole bunch of structural complications, and there's a whole bunch of things that can go wrong. So we're going to talk about why here tonight, and that's going to be the idea. But first things first, I want to shout out to the chat. We got Mr. Will Stevenson from the DGen Roundtable in the chat. Y'all, check out the DGen Roundtable if you want to learn about cryptocurrency, because it's a cool place. Thanks, bro, for showing up and showing your wonderful support. Good to have you on. Thank you, good brother. We are going to jump right into it here. So the first thing that we should know is, what is a gambrel roof? So if we were to draw a regular house, that's a box like this, and we put a roof on it, that would be like a regular house. A gambrel roof would be as if you took the roof, and instead of pointing it up like that, you are going to come up at a steeper pitch to start on both sides. It's not curved. And then you're going to change the pitch about halfway up. If you're used to seeing like sheds and small backyard barns and things like that, or like a big barn, this is the type of structure that's used to make that. Now, if this was a shed, this would not be particularly complicated of a structure. There's probably some metal spars that run back and forth that are shaped out to hold that up, and it's not complicated. And if this was a barn, it's probably very large, and below each one of these corners is support probably all the way down to the ground via various beams and posts. So it's probably something of that support, of that sort, for like the load path of how the ridges are held up. So that is a gambrel. Now, what is a vault? For those who don't know what a vaulted ceiling is. So if we were to take a house that has a flat ceiling and it has a pitch like this, some people want to do things where they are going to want more volume. They want the inside to feel bigger. They want the ceiling to get taller. And there are various ways by which you can do that. One of the ways is you can vault the ceiling up against the rafters, which are these structural members that are making the roof. So let me blow this up actually just a little bit bigger so we can all see what's going on. So if I make this, that's bigger. So if I make that the roof, then if we had a flat ceiling, that ceiling line would be here. But we don't want a flat ceiling. We can do one of two things in this particular scenario. We can either vault the ceiling all the way to the roof, in which case there'll be a nice big load-bearing beam at the peak that will run down the room. If you've ever been inside a vaulted ceiling, I'm sure you've seen it. That is one way to do it. The other way to do it is create a false ceiling, which is a real ceiling. It's just lower pitched. And so there's benefits of creating a false ceiling where they would basically take this beam, they'll drop it down lower in the attic, and they'll run their ceiling to that and then down. And the benefit of this is that you now gain, use a different color, you now gain attic space. So you can fit more insulation up here, and you can run more ducting, wiring, plumbing, all of the things that might need to go through somebody's attic. So that would be a false ceiling. It's still a vaulted ceiling because the ceiling's not flat, but the ceiling has not been vaulted to the roof member itself. So that is a vaulted ceiling. Now, that is a very simple scenario because we're dealing with one pitch versus another pitch, and they're coming together at the peak. All of the loads are very simple. If we were to draw that scenario, we have a beam at the top, a wall over here, a wall over here. We can still see everything, I hope. Yeah, it looks like it. And then each member is going to sit on the wall. It's going to come over to the beam. And it's probably going to have some kind of joist hanger or something that's holding it. It's got a seat cut right here. And it'll run back to the wall, and it will sit on the wall there. So we got a download right there and a download right there from this member, putting weight straight down onto this wall and weight straight down onto this beam. And of course, there would be one on the other side as well. So that's a super simple loading scenario. Now, the thing that we have to deal with a Gambrel roof is we don't have that simple loading scenario because remember, in a Gambrel roof, we had our two walls and we changed the pitch halfway up. So what we did is we created a hinge point right here. Well, what does that mean? Well, it's like, well, let's think about how this would be constructed. If you were to do a flat ceiling, this would not be difficult. You would essentially probably just run some kind of beam down, like if this was like a, let's say it's like a 20-foot long by 8 or 10-foot wide shed, right? You could just run a beam or something down the middle of this, and then each point of this could be braced down to that beam. And that's going to hold all of the weight in place. Everything's going to get covered in sheathing. It's all going to connect together and be super strong and stiff. So that's easy. Now, if you were to try to recreate this scenario, but you were going to try to do like a Gambrel roof with a vaulted interior, we could take that beam, put it a little bit higher up. Now you have this pitched ceiling on the inside with two pitches like that, but you still have this like barn-looking thing on the outside, the Gambrel, right? Well, that's easy to brace that down to here, but now the problem that we have is that this load, this is becoming too sideways to actually really support what's going on here. And so this would not be an appropriate way to do this. Once this goes over a 45-degree angle, these braces become kind of like, don't do it, don't build it that way. So we don't want to do that. But that's not the scenario that these particular people were going after. They wanted the vault all the way up to the outside of this guy. Let's redraw these walls. So what would that scenario look like? Well, it would look like this. They have a wall and a wall. They're going to have their peak up here, which is probably some kind of ridge board or whatever. And then they're going to have, I mean, there's any ways to make the cuts however you want, but let's just presume they're going to run up to here and then run up to there. And let's just say that they were going to butt these right into each other. You could do the math and then like splice it with a piece of plywood or something if you wanted. Depends on how you want to build this. Some people will do like a hand-built truss on the job site so that this can be done strongly and stiffly. Let me check the chat real quick. We actually had an Instagram chat here. When the photo's coming out from Spider, Knox Clements, if you're still watching this, check my story on Instagram. There's a link on there that has a Dropbox for all the photos. That's where it all is. I'm going to repost the link for a few days. So that's where it is. And actually what I'm just going to do, I'm going to write down Knox down here in the corner. And I'm just going to send you a DM after I'm done here. So there's your answer, Knox. But this would be one way to frame this if it was like a slice, right? So what do we got going on? Well, we have our wood member sitting down on the wall, but the other thing that's happening is because the wood member is at an angle, the true support is, it's pushing like, let me use blue here. The true support is pushing down like that. Like that's the real load because this thing is at an angle. So if we took this arrow and I superimposed it and I just put it right here instead, what we have is this little red guy right here. And that, well, it's not really well read. It's pointing left, right? It looks like that's cut out of the Instagram just a little bit, but you'll get over it. So it's pointing left, and what does that mean? Well, if we have one on both sides of the building, then what's happening is these walls are trying to tip out. And that's not good. We have to resolve that somehow. So that's our first problem. Our second problem is that we have the exact same thing happening right here. Because if I were to show you, this board comes and hits this board, and it puts that force on it. And that force consists of that guy plus, let's take the blue arrow. We're going to copy him and just put him up here like that. And that gives us, we're going to use green for this one. We have this little green arrow right here, and it's pushing that way. So what's happening here is this thing is trying to bend and fold out that direction. So what we've essentially done is we've created a system, this wood frame that left alone with just some nails and very weak joints, when you apply roof material to the top and a snow load or people up there or whatever, what's happening is all of the weight that's being pushed down right here or weight that's spread across the roof is trying to basically collapse the entire assembly. It would basically look something like this. That was a terrible way of doing it, but like it's going to squish down and flex out and just collapse and be bad. And we don't want that to happen. So that is one of the problems. And so one of the things that happens when you vault a ceiling is that you are trying to not put stuff up there so that you can use the space. In this particular ADU they were doing, they wanted to use it as a loft, which means they have to be able to walk around. What would be an easy way to get around this? If we had our Gambrel with, I'm going to get really good at drawing Gambrel roofs today. If we had it like this, we could vault the upper part, but every like 4 to 6, maybe 8 feet of our roof, or like down the building, we could install a big, beautiful timber truss that's like built to do its job of supporting all those elements. And what that does is that would allow us to put a cool visual member in. We still get the volume from the vault, but we would lose the ability to walk around up here without having to climb through this truss thing. So that would be a cool way to do it and easily support everything, but that's not, unfortunately, what they were able to do. So we have that problem. And not only that, but everywhere you make a hinge, like as soon as you vault the ceiling, you need to apply sheetrock to the bottom side of your rafters. I knew a lot of builders who were very hesitant to use the rafter member as the sheetrock carrying element. And part of that was because there's all kinds of things that happen on the roof, and the roof is exposed to all kinds of intense temperatures and all kinds of craziness. And so what would this look like? Let's say if you were, well, what I'm talking about basically is like if this was a top of a wall section and this was a normal ceiling joist that's going across, and this would be our rafter going up. What we would want to do as a builder generally is apply our roof sheathing and our roof decking up top up here on top of this guy, and our sheetrock would go underneath here attached to this guy. And when you do a false ceiling, which is basically taking this ceiling joist and turning it and making it go up, the sheetrock is still attached to a separate member as the rafter. And that's good because like if someone right now, in this example, if you've got a 400-pound dude up there moving shingles around on your roof and things are heavy, you have this massive load that's being pushed around in different places on the roof. And I can tell you the way we size these rafters for a roof by code is, I think it's like length over 180 is the allowed deflection. It's very bendy, right? We won't want that amount of bendiness for a ceiling that's got sheetrock on it. Now, all that stuff is in the IRC, it's in there, and it's adjusted in the tables. But we don't want to try to be bending sheetrock because when it's taped and floated and it's all good to go, you start bending it, you're going to start cracking it. So I knew plenty of builders that wanted to keep these separate in every way they possibly could so they could avoid the sheetrock cracking, because that's just more crap to come back and fix. So if we're doing the Gambrel roof, we don't have a ceiling member. We just have the rafter that's going up and doing its thing. So what does that mean? It means our sheetrock is going right up against this guy. Now they're probably not curved, but that's okay. Now what other problems do we have here while we're talking about it? So the other problem this gives us is that whatever this member is, that is the space that we have to do two things. One, it's space to ventilate, and two, it's space to insulate. We have to accomplish both things in the depth of this member if we're going to try to vault up against this. So, well, why do we want to vent? Well, we want to vent because on a normal day, the sun comes out. And the sun comes out and it puts all its happy sun rays on the top of the roof, and it heats up that asphalt. And then what happens next? Well, that heat tries to radiate down through the members. And in a regular house, what would happen is, let me draw a new cross section here. Let me show you venting in a regular house. So in a regular house, what you'd have is, this is the top of your wall. You would have your rafter going up, doing its thing. You'd have your ceiling joist going over for your ceiling. And then this would extend and it would box out some kind of soffit or eave around the edge of the roof. And the real member is like this, and this is usually a block of wood of some kind, like that. So what do we do in a regular house is, with a regular attic, is we want to vent and let all the regular outside air through this assembly so that all of that heat that's coming down through the roof can go into the air that's coming through the attic that's also leaving the attic. That way the heat doesn't stay up there and then radiate straight down into your house. That would be no good. So air likes to go from cool to hot. Well, that's not true. Air, when it's down here, is cool air because it's under the eave, it's having a good time. Air that is in the attic up here is starting to get warm. And what do? We normally put a vent at the top of our roof so air can come out, and then we vent, we put holes in this thing down here so that air can go in. And what does that allow us to do? Air can go up here. It usually passes right over this wall through here, and it goes up into the attic, takes all of the hot air out and brings in cold air. So that's a good thing. We want that to happen. That avoids moisture problems. It keeps the attic a reasonable temperature, and it keeps the house from having to fight. It keeps the ceiling insulation from having to fight the radiation of all this craziness that's coming down onto the roof. So in this scenario, it's good because we have a venting attic. In the scenario of the Gambrel roof, we do not. We just have our rafter member, wall rafter member. We have sheetrock right here, and we've got roof sheathing right on top of this, making the roof. And so how do we vent this? Well, maybe you just don't, but like you'd have to have some kind of detail or something over here that's designed to let air in right there. Sometimes it's like you drill holes and you put these little like screen things in. There's just all kinds of ways to do that, but you let air in here so that air can pass through a channel that's up here. And there's a product for that. It's like it's a foam or a cardboard or whatever you want to buy, but it's got like this 2 V grooves on it, and you basically staple it up to the sheathing, and it lets air pass through this. And that's like the equivalent of trying to let the roof deck vent. So that's that. And what does that leave us with? Well, that leaves us with all of our insulation. This is how we formally draw insulation in the drawing world. So that leaves us with our insulation right there. So not a lot of room. Structurally, if you're doing a shed or something small, you really only probably need a 2x6 to do this. But for insulation purposes, you're going to want more than that, because getting less than 5.5 inches of insulation, you're probably going to get 3 or 4 maybe at the most because of the venting. That's not enough, especially if that's your entire ceiling. And we don't want to do that. So that's the other problem that's going on with it. What else is wrong with it? Well, so like I said earlier, because the sheetrock's attached to the roof, and the second anybody's walking around, dropping the marker. The second anybody's walking around on a roof, you're going to get a bunch of load up here, and this thing is going to flex. And it's not so much that the sheetrock might break along here, it's that you're going to notice it in this joint. Potentially, there's movement there. So kind of depends on how everything's been mudded and painted and stuff. And sheetrock cracks, things move, houses shrink, wood stretches and expands and contracts with moisture content. These things are not all perfect. This is the world that we live in, but these would contribute to it being a worse idea. And so we would just like to not do them. So we talked about structurally why that would be difficult. And we talked about insulation and venting and all of that stuff to go on. Let's talk about how we could potentially fix the structural part. So let's say they're going to use a nice deep member that was 12 inches thick, get a lot of insulation in there, and the venting was no problem. They still got to fix the structural problem. How would they possibly fix that without having a member visually displayed on the inside of the building such they could walk around and make a usable bunk room or loft space? Here's how we would do that. So the problem we were experiencing was both at the wall and halfway up the roof where the pitch changes, we have introduced a joint. So when you add lots of weight to things, falling over. When you add lots of weight to things, all of the nails and the flat connections and everything tend to not matter anymore. And things are treated as joints. So let me see if I can do this here. So if you ever played with Legos or Connects or things that have joints like this, then you could imagine that there being 5 different places where any of these can rotate in any direction. This could rotate this way, this could rotate this way. This thing would be super wobbly, right? Not a good idea. So how do we do that? Well, the only way to do that in a hidden way is to either build this entire piece out of one piece of material that has built-in strength and it wouldn't have any way to rotate because it's one piece, or maybe if it's steel or something that's been bent and formed, or steel that's been bolted together, you could do that. But if it was just wood, how would I approach it? Well, I would probably try to use steel plate of some kind if I was trying to be fancy. So one of the joints would look like this. We have this angled cut and we have another board coming off like that. So that is the joint that we're dealing with. And the problem is that this thing wants to pivot, and it's either going to pivot about the inside point and it's going to spread open and there's going to be a gap that forms right there, or it's going to pivot back the other way and there's going to be a gap that forms down here. How do we avoid that? Well, we can build or fab a metal plate that was big enough and extended long enough into each piece of wood such that it develops, have a nice big aggressive nailing pattern in it so that you can develop a lot of shear between the plate and the wood, make them bond as one, and then put this on both sides, most likely. And what's going to happen is this metal plate is going to be doing the work of keeping these wood pieces from twisting past each other. So that would be the way to do it if you wanted to try to do it hidden. But if you're a builder, good luck getting this to fly. If you're in a city trying to get a permit for something like this, then a city inspector and or the permitting department is going to want to know, an engineer is going to want to prove why this works, especially if it's for a bigger building. And if that's the case, then you have to get an engineer to hand calculate this thing, which engineers are used to doing a lot of simple things and using a lot of relatively straightforward math systems and stuff like that. If you give them a custom job like this, it's hey, our building is this size and we got to go in and prove this thing. That's going to cost a few $100s at least, and possibly a few thousand. So that would be the way to do it. If you wanted to know how to do it, I have lots of other videos on my YouTube channel that explain structural engineering and between woods and nails and stuff. But you'd essentially, you'd try to figure how's this thing going to rotate and where. We'd say that it's going to rotate right here. And what's happening is now about this point, every single nail through the plate looks like this. I'm going to draw a cross section. So here's our plate, and our wood is 1.5 inches thick, and we have a nail head and the nail. So everywhere this is happening, the nail is preventing shear between the steel and the wood. So there's a force that's attributable to that nail. Let's just call it 100 pounds of shear across that nail to steel to wood. It depends on the steel, it depends on the wood, it depends on the length of the embedment, it depends on the nail diameter, the nail material, all of these things. But you'd pick something, probably something that someone's likely to use, like a standard galvanized 10-penny nail or something like that. And then you would look at this force. How far away is this nail hole from that rotation point? How far away is this nail hole perpendicular to that rotation point? How far away is that nail hole to that rotation point? And what you're going to do is you're going to add them all up, and you're going to determine that based on the weight of the roof pushing this down and the angles of the roof that we have, there's some kind of twisting moment, we would call that. There's a torque applied to this point that the roof is trying to crush and fold this thing in. There's a torque going out. Let's just call it, I know this is correct. Let's just say it's 100 inch-pounds of torque, right? I have no idea how much that is. But if that's the number, then we just need to make sure that if we have a nail that is 100 pounds of shear and it's 1 inch away from this point, we have now put something in that has enough strength to withstand this torque. So that's how you would calculate that if you wanted to hand it to an engineer. So that was a little bit in depth on how I'd approach the situation if I absolutely needed to build this and there was no other way of making this happen. Hopefully this is useful to you guys. I just wanted to share this fantastic little experience and bring to light all of the wonderful things that people may or may not know about when designing a house that you would come across. So that said, thanks to everybody that's watching. Thanks for coming on, and let me know in the comments if you guys ever have any specific questions. And we're going to take it out with some music by the one and only Highway 6 Band. Shout out to them for giving the license to this music. Thanks guys for watching.
Same set list every day, Saturday night.